The geometric properties of spatial data are defined by how the data is represented, so for example point, line or area. But it's not solely defined by what you're trying to represent, but also the scale at which you're trying to represent it, the scale at which you're trying to do your analysis. So for example, if I were using transport routes between cities in a country, then I might use point locations for my cities. But if I was actually analysing bicycle paths within a city or walking in Memphis, then I would represent that city using a polygon. Geographic scale therefore plays an extremely important role in spatial data and analysis. Scale is related to the analytical goal, which in turn determines the geometric properties of your data. And remember, the more real estate on the screen means a smaller scale map, and vice versa. Geometric properties use coordinate information and include information about the position and also measurements such as the length, direction, area, proximity and volume. Proximity or distance allow us to find what's nearby. And although distance is often expressed in units of length, time and cost are other examples that we could use in which we could measure distance or proximity. So for example, how long does it take to reach downtown, or how much does it cost to fly from one city to another? Using a GIS, you can easily measure straight line distance, called Euclidean distance, between target and source features. You can also create buffers, which are zones of equal distance, fixed radius around target features. Within those buffers or search areas, we can use these to search and look for other source features. You can buffer around points, lines, or area data. Remember though, spatial data represents the Earth, and the Earth isn't flat. Actually, strictly speaking, it isn't round either. It's actually a lumpy spheroid. Computer screens and paper maps don't really come that way. They tend to be flat, and they'd be rather tricky to use if they did come as spheroids. So mathematical transformations called projections are used to translate from a spheroid to a flat surface. In doing this transformation, the reality is always slightly distorted in some way. So it's almost impossible to squash a curved surface to a flat surface without some kind of stretching, shearing or tearing. So let's look at one example. Most online maps tend to use Web Mercator. That distorts the shapes and the sizes of the land masses and the oceans profoundly, particularly as you go towards the poles. So why then is Web Mercator used so widely? Well, it was designed as an efficient way of working with map tiles. It allows you to work at multiple different scales and do rapid panning and zooming across that data. It's a projection that preserves angles, which is why the original Web Mercator was designed to allow sailors to navigate around the oceans. So it was making sure that those bearings, those angles, took them in the right direction. It's not really designed for much else, and all the other distortions have been trumped by the need for computational efficiency. For analysis though, distortion is very important. So in your analysis, if distance is very important, then make sure you choose a projection that minimizes the distortions of distance. Are you using areas? Choose a data with a projection that minimizes the area distortion. There are other different types of distortions, so make sure that you use a projection that's correct for your analysis. If you're doing analysis over very small areas such as cities, then your projections become a lot less crucial. But if you're doing analysis over continents, oceans, or the entire globe, then it becomes very important. They're going to have an impact on the results of your analysis. And of course the maps will look very different with different projections. Try searching on map projections to see some of the ways in which the spheroidal Earth is represented as a flat surface. So your analytical results are particularly important if you're going to represent them as a thematic data, as a thematic map. It's quite likely that you will when you're doing analysis, because the thematic maps actually allow us to show information about places. That tends to be what spatial analysis is about. So remember, your map's going to look different with different projections. So using spatial data allows us to analyse and better understand the world. We can describe information by location, and we can query attributes to provide more detail about those places. But doing good analysis is really about the question. It's about what scale you're going to do in your analysis. What is your analytical goal of actually doing that? That's what leads you to getting a meaningful answer to your analysis. You should better understand your data. You should query that data, get descriptive statistics for that data. You should also understand how the decisions you make impact upon your analysis. Effective analysis goes way beyond actually just picking the right tools for your analysis. It's also about how the results are interpreted and how you share those results with others.